Hello and welcome to day 11 of the Advent of Code 2022. Let's go and read this statement. Okay, is this the input? Let's check the input first. Okay, the input is pretty short. I think it's so short that we may want to just copy and paste what we need to do instead of parsing this input. Let's see what we need to do. We have this explanation for its monkey 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7. Okay. Starting items, operation, new equals old, test, if true, if false. Okay. Starting items, operation, and test. After each monkey inspects an item, but before it tests your worry level, you will relieve blah 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 divided by 3. Okay, so it seems this we need to do always. The items take turns. Okay, so let's see what happens. So monkey 0 starts and inspects the item of worry level 79. That's the one. The bad thing of not parsing the input is that we'll have to paste both the example and the real input if we want to simulate this. So what happens is the monkey inspects an item, then is multiplied by 19, because I guess this is what we were doing. Then the monkey gets bored, it is divided by 3, and then if it is divisible by 23, I guess if it is divisible by 23, it goes to number 2, otherwise it goes to 3. Okay, so I think we're going to just run this. Sorry, not Python. I always do the same mistake. Okay, so let's do monkeys equals. I think we're just going to paste this thing. So we're going to say items and paste a list. It's going to be this. We never know if this is going to be a good idea or a bad idea, right? So we have 8 monkeys. 1, 2, 3, 4, 5, 6, 7, 8. And the items are this. You never know if you're going to waste more time or use your time wisely by copying the input. Anyway. So these are the items. Then we have the operation. So the operation could be a lambda n. What do we do? This is n times 17. So this, let's copy this operation. Okay, so this is n times 17. This is n plus 7. This is n times n. This is n plus 1. This is n times 3. This is n plus 4. This is n plus 8. And this is n plus 6. So those are all the operations. And then all the tests are whether something is divisible, right? So we could call this something like next. It would be a lambda n, and it would be 3 if n modulo 11, else 2. So this means if n modulo 11 is a positive number, is not 0, So if this was 0, it would be the else case, which is it goes to 2, which means it is divisible. Otherwise, we go to 3. I think this is what we want to do. So let's copy this, and then it is divisible by 11, divisible by 3, divisible by 5, divisible by 7, divisible by 19, 2, 13, 17. And then the next ones are, so 2, 3, 5, 6, 7, 1, I mean the 2, 7 is 2, 7, 0, 3, 6, 4, 4, 0, and 1, 5. Okay, so now we have parsed all of the input. Let's see what we're asked. So what is the level of monkey business after 20 rounds of staff singling? Okay, what is the monkey business? What is this? Changing all the monkeys, you're going to have to focus on the 2 most active monkeys. Count the total number of times each monkey inspects items. Okay, so this monkey inspected so many items, so many items, so many items. Okay. So I think we need to simulate this for 20 rounds. So let's say for round in range 20. And what are we going to do? We're going to run this simulation, right? So each monkey, so for m in monkeys, what we're going to do, and maybe even with for I in enumerate monkeys. I don't know if we really need to know for item in m items. So for each item, what they're going to do is first apply this operation. So we're going to do item equals m operation of item. First we apply the operation day, then the item is divided by 3. And then we check this, and then this is thrown to whoever it goes. So then I think, well, we need to pop this item too. So, well, instead of popping, what we can do is m items is going to be an empty list, right? So, and now we have to choose and move it, so it will be monkeys m next applied to item. So this is because the current worry level, which is 500, is not divisible by 23, I guess. So this is the next of this dot items, or not dot items, sorry, items dot append item. I think this is what we want to do. And then we need to count how many inspections. So inspections is 0 initially, length of monkeys. And this inspection, this will be inspections. Now we use the I in this enumerate plus equals 1. Print inspections. Let's see. Okay. And we need to take the ones, the 2 that are higher. So we need to sort this. Sorted. And we need to multiply. So from math import prod, and we have to do this, the product of the last two. I mean, this is a bit, well, it's a way of doing it. I think we're going to submit this, but I don't have much faith. Okay, it's right. Very good. I'm very happy, because otherwise we would have needed to paste all of the example and debug, and that would be terrible. Let's go for part 2, and then we will do some nice refactoring. Okay, part 2. What is this? So in fact, blah blah blah, no longer causes your worry level to be divided by 3. Find another way to keep up your worry. Okay. You might be putting up these monkeys for a very long time. 10,000 rounds. You can still figure out the monkey business after 10,000 rounds using the... Okay, so now it is 10,000 rounds, but without dividing by 3. So are we going to copy this and run this the same? So instead of, oh yeah, this is the length of monkeys. Instead of this, it is 10,000 rounds, but we're not dividing by 3. We're not dividing by 3, I think. Blah, blah, blah. No longer cause your order to be divided by 3. Fortunately, that relief you want to from... Find another way to keep your worry levels manageable. Okay, I think this is just some... Is this thinking? I guess this is thinking. The simulation is probably taking some time. Is expected. You'll need to find another way to... Starting again. What is the... After 10,000 rounds. So what is the round? Well, round is a... So let's print R. Okay, this is a bit slow. Why is it so slow? Okay, I think we need to think of a... Like simulating this. Simulating this is not feasible. So we need to understand this algorithm better and do something with it. However, it's weird that are the inspections growing so much? Oh, wait. I'm running this. Let's ignore this for now. Okay, now this is going a bit faster, but still. Okay, so why is this going so slow? Why is this going so slow? Inspections. These are some large numbers. Now I have a crazy idea, which is using another Python runner, but for sure there must be some easier algorithm. Like there is some greedy algorithm or some way of doing this faster. So we need to think what we're doing. However, there is this Numba library. I don't know if this works, but I had some good luck in the past running this Numba, so maybe that would be a good way of solving this. Anyway, so this would be, I don't remember how this Numba worked, so import Numba. So this would be def simulate return inspections. So this would be, inspections equals simulate. That, okay. So this would be pipenv run python 11. Okay, that's fine. So now, what about numba? Numba dot, what we can do is pipenv shell, sorry, numba dot, how do we use this numba? Python numba. How do we use this? Ngit. So this is from numba import ngit. Monkeys cannot type list element class dict. Okay, I guess this has some limitations, but maybe this is just a matter that this should go inside the function. Is that the issue? No. List. Okay, I guess this has some problems. Numba list of dictionaries. Dict. Unsupported constructs. Okay, so dicts are not supported. Okay, so if dicts are not supported, lambdas, I'm not sure if they will be supported. So let's think. Let's think if there's a better way. Probably, I mean, for sure there will be a better way. I think using this could also work. But so what are we doing? Are we maybe, could we do some kind of memoization? So are we maybe, let's undo all of these changes. Okay, so here we are. So let's print, let's have this scene equals a set, and we're going to add scene.add tuple of m items, and then we're going to print tuple m items in scene. False, 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 false. There are some true cases, but it's not like we're all the time doing the same. So I'm not sure if that memoization would be so helpful. It's weird why it starts going so slow. It's like at some point it is not advancing anymore. I don't really understand why. Let me print the length of m items for m in monkeys. Yeah, so it's not like the number of items is growing or anything. Okay, so what we're doing, the algorithm is the following. 10,000 times we are listing all the monkeys, getting the items, increasing the inspections, applying this operation to this item. And then we are appending to this list, and we are truncating this list. So the point is that the outcome for each item, okay, let's have this fast, let's say have this 2 is going to be a dictionary for now. I don't know if this will help, but this 2, what we're going to do is for item in blah, blah, if item in M2, then what we're going to do is monkeys, let's say 2 equals M2 item, monkeys2 dot append item. Continue, right? So we are going to say, and then here what we're going to say is monkeys, not monkeys, but M2 item, not item, but the original item equals item. So original equals item, original. Okay. So what is the problem? Monkeys2, okay, not monkeys, yeah, 2. M2 item, no. Yeah, the monkey we're going to is this one, the next item. Monkeys 2 items dot append. Okay, this is exactly as slow as it was before. I still don't get the idea of why this is so slow. So I'm missing something here. I don't understand why it is so fast in the beginning and so slow in the end. I would think that so this does not help. So let's think a little bit more. So here we have these starting items. So each items always ends up being converted to another one and going somewhere else. But for example, let's see what this means. Okay, old is multiplied by 17 if divisible by 11 goes to 2 or goes to 3. I see. Okay, this item is divisible by 11. This item 2, this item 2. So there are some items divisible by 11. Divisible by 3, for sure there are some that are divisible by 3. This one is divisible by 3. So I guess items, let's see what these items look like. Instead of length of items, let's print the items. Okay, that is the problem. The problem is that items are huge, but don't we have to do some kind of... Okay, URLs are no longer divided. Okay, but you need to... Now I get it. So all you need to do... Okay, now I understand. So the problem is that the numbers are getting insanely huge. Okay, so that is the issue. Okay, That is the issue. Now I understand. Okay, let's see where we are. Okay, here we are. So what do we need to do? Well, we need to keep numbers. So the divisibility by 11 is the same, by 3, by 5, blah, 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 blah. So I think what we need to do, instead of dividing by 3, and now I understand why, we're going to divide it by 11 times 3 times 5 times 7 times 19 times 2 times 13 times 17, but not divided 2, but modulo equals. Is that what we're going to do? What is the problem now? Print R. Wait. Now this is growing. Okay. We get this number. Let's try to submit it. Oh, we got the gold star. Okay, so that was the issue. I wasn't understanding why the numbers were getting so long, but now it's clear. So the way to run this simulation, what we can do is we can say, okay, we could have this simulate, and here we could say limiting function. Okay, so the limiting function, we could say item equals limit or reduce. How would we call it? What is this being called? Okay. Let's say, I don't know, F. Let's call it F for now. So in the first part, what we're doing is we're going to simulate with lambda n divided by 3. That's what we're doing in part 1. And in part 2, what we're doing is n modulo all of this. All of this. And then here, this is inspections equals this, inspections equals this, and we print this. And we print this. Let's see if this works. Okay, simulate is not defined. Okay, simulate goes up here. Li item equals li. Okay, f of item. No printing. Okay, and now we have here the n, and because we're running the first time, we run it 20 times. The second time, we're running it 10,000 times. Okay, let's see if I got this right. Yeah, this is right. So this was, so this was P1 equals this. Instead of this, we could say sorted we could just dot sort, and here we could say inspections -1 multiplied by inspections -2, and here we assert P1 equals this. We could do the same or similar for P2. We assert that P2 equals whatever we submitted here. This is part 2. This is part 1. Okay. Oh, because this is not inspections.sort. Is that the thing? Assertion error. Okay. The second one we didn't get right now. So what is print p2? What are we getting now? Okay. Inspections.sort. Oh, because we're modifying the monkeys. We're modifying the monkeys. So here, let's say monkeys. This is not going to work, I think, because we are just sending the same list and still things are modified. So I think we could, one thing we could do is import copy. So this could be copy dot deep copy. Okay, this is working now. So ideally we would do the same here, but we can now later think if there's a better way of doing this. But well, anyway, we got rid of this. So I don't know, maybe this is better to have this. We have this sort and -1, -2. In the past we had math.prod sorted inspections -2. This is what I had before. Maybe it's better. We don't need the sort. So yeah, maybe, this is better. Okay. Is this working? No. Sorry. This is not working because it is sorted inspections and then we take the -2. So first we sort the inspections and then. Okay, now this is working. So what we want to do now is we can improve this simulation probably. We could improve this simulation. Here we read input to, or convert input to a list of dictionaries. So this is what we converted this to. This is the list of items. This is the operation. This is the next monkey that we use. Instead of having this, we could maybe do it differently, but let's leave it like that for now. So we have initially, these are the number of inspections are this, 0 times monkeys. Then we enumerate all of this. We add for each item, we add one inspection. We apply this. So here, this f would be limiting function, something like that, limiting function. So what we're doing in the end is we are applying the operation, then we are applying the limiting function, and then we apply the next function. So we could even say here next. Well, next is a built-in function, so that's not a good name, but we could say next equals this, and then we append this item to the next items, and finally we remove this list. So we empty this list of items. Is there a better way to do this? This is a pretty short code already, so I think it's good to have these steps separated. Here we could also say, so inspections plus equal length of monkey of m items. So if we just add, sorry, inspections I. So this is one way of doing this. We could also even list it. So for each monkey, we are just adding this number. We could also say, you know, inspections in zip inspections, or even the opposite, right? Monkeys inspections and we could say here, no, but this is not going to work. It's not going to work because we're not updating the list. We need to take the index. This works. The good thing of doing this here is that we are only having one operation inside this loop, which runs many more times. So it's just a small optimization, let's say. So we update the inspections, then we have this item. Of course, we could do this, you know, limiting function, apply both things at the same time. Limiting function, and then, so we have the operation, then we apply the limiting function, and then we take the next item, right? So this, again, we put it in a different line. Whether it's needed or not. So the new item, we could also call it that, you know, the new item, new. Initially, what we do is we apply 20 rounds and we divide by 3. And here we apply this 10,000 rounds and we divide by this, which in fact are all of the prime numbers lower than 20, right? So we could say 2 times 3 times 5, 7, 11, 13, 17, 19. This is the same, but it is shorter, so I like it better. So this copy of the monkeys, we could also just, we could put this inside the simulation. It's a bit ugly, but we get rid of the copy. We just okay, limiting function. We forget about the monkeys. Not ideal, but we could say, we could also have def monkeys, and we could return this. So we have the we have the simulated function. The simulated function has one purpose in this case, so it's not, but we don't have to copy. So now we have, instead of simulate, we could call it number of inspections. So, well, it is simulate, in fact. So we could add a comment where it says simulate the monkey's behavior and return the number of inspections they did, right? So this number of inspections, it is 0 initially, then we simulate its round, and then we iterate for its monkey in its round. We add to the number of inspections the number of items they have. And then, I don't know, do you like this better, or maybe just inspections I plus equals 1? It's like less to think, maybe, if you do that. Then we have the limiting function, which initially, instead of n, we could say rounds. So initially we were dividing by 3. Then we're doing this modulo of all these numbers, of all these prime numbers, so the numbers don't grow, the items don't grow exponentially. And maybe, what else could we do? Well, I think this is a nice trick of having these lambdas inside these dictionaries. We could have a name tuple to define its. But I think, and here, if we deleted this, we don't want to put this in a single line anyway. So items up next. So for each m of I, one thing we could do, instead of doing this, instead of having this, we could have a tuple like this. I think it is less clear what you're trying to achieve if you do this. But if we did this, here what we would have, let me rewrite this function, how it would look like. So for me it would be I, and this would be items up next in enumerate monkeys. So here we would say for item in items, inspections I, and this would be operation, and this would be next underscore, and instead of items, this would be the first element, right? So is this clearer than this? I don't think so. I think it's helpful to see where we're at. So instead of this, this would be items again. We remove this monkey, but I think it is not a good idea. So let's undo these changes. Go down. Let's do this. We're not really reading, but you don't really care. When you read the monkeys, you get a copy of the input, and that's it. Okay, so maybe we are done for today. I was a bit I didn't understand what was going on after the first part. So the second part, the numbers were growing very much. I read this where it said find another way to keep your worry levels manageable. but it was useful to print the items and find that they were growing too much in order to understand what the problem was. Using this number module that I tried could have been useful, but it doesn't support dictionaries, so it is more limited to more kind of numerical calculus. Well, this is it then. Let's see what lessons we learned today. So one trick that we have used is this of using, well, we just copied the input instead of parsing. I think this was a good call. Second, we used dictionaries of lambdas. So we could have had this, if it's a plus, do add, if it's this, do that. But then we have this operation, and this operation is applied, which is a lambda. For n, it is n plus 6 or n plus 8 or n plus 4 or n times n. And then the next is also a good one. It's just a lambda that does this. So maybe now that I'm thinking, we could even like put this together in a single operation, but I think it's not necessary. So what we could do is, we might want to do that, but I think it's unnecessary. One optimization we try to do is doing this memoization of where this item is going, but in the end it didn't seem so helpful. Okay, so we use dictionaries of lambdas to apply different functions for each monkey. Then we used, again, math.prod. We have used it in the past. We used, of course, the important trick here is that when you are checking the reminder of dividing by 11 or the modulo 17, etc., you can do this modulo all of these numbers, and the result will not change. So when doing modulo all of this, keeps the result equal for operations like modulo 11 or modulo 3. So that is the key insight for doing the second part. What else did we do? Well, I don't know. It's important. We saw that we need to copy the input twice. We could do that with the copy. We could do it with copy dot deep copy. What we did is just use a function that returns this value, and we call it twice, and that's it. So that's the other solution we found. What else? I think this is more or less, this is it. Today's problem, it was nice. We had this hard to parse input. I just decided to copy it. But we got the stars at the first try, so we cannot be angry with it. Let's leave it here. Have a nice day and see you tomorrow.